I'll be continuing here on 4.3, derivatives and the shapes of graphs. All right, so everything's on there. Okay, we have number 25. So this problem's going to take a little while. We have the function f of x equals x cubed minus 12x plus 2. And we're asked to find the intervals where it's increasing and decreasing, local max, local mins, intervals of concavity and inflection points, and then to use all that information to graph the function. All right, so here's what I'm going to do. It's pretty much what we've been doing in the previous problems with one kind of added step at the end. That step's going to be pretty long, but we'll get through it. Clean this board up just a little bit. And I apologize, I'm still not completely cleared up here, so it's tough for me to talk. All right, so let's start out. We're going to need the first and second derivatives to do this. So let's go ahead and get the first and second derivatives. The first derivative of this function is 3x squared minus 12. The second derivative of this function is 6x. All right, so let's find out where the function's increasing and decreasing. So we're going to take the first derivative, set it equal to 0. So we take 3x squared minus 12, set it equal to 0. This is 3x squared equals 12. X squared is 4. So x is plus or minus 2. So we solve that little quadratic, and that gives us two critical numbers. We look at where the derivative doesn't exist, and this doesn't happen because our derivative is a nice polynomial. So now we go about setting up the number line. We place our -2 and our +2. These are critical numbers. And then that breaks our number line into 3 sections. So I'm going to pick some test points. So how about like -4, 0, and 4. And I'm going to plug those numbers into the derivative. So I need f prime of -4, f prime of 0, and f prime of 4. So if I plug -4 into the first derivative, -4 squared is 16. 16 times 3, take away 12. That's going to be a positive number. So I'm going to get a positive number here. The first derivative being positive means my original function is going up here. Then we plug in 0. If we plug in 0, we get a negative number. So it's negative. That means my original function is going down here. And if we plug in 4, we're going to get positive again. And that means our original function is going up. Since these two numbers are actually in the domain of this function, those are dots, those are points on our graph. That means that when we go up and down, that will be a local maximum. When we go down and up, that will be a local minimum. So let me talk about first where it's increasing, and I'll put this information over here. Our original function f is increasing on the interval -∞ to -2, unioned with 2 to infinity. Okay, so that's everything here and then everything there. Our original function is decreasing on that middle part. That's from -2 to 2. Let me just check this real quick. Okay. All right, so we have a local max at -2, So that's when we get, this is a point, negative 2 goes into the original function. When I plug negative 2 in here, let me see, I get negative 8, I get plus 24, and then plus 2. So negative 8 plus 24 is 16, plus 2 is 18. So that point right there, negative 2, 18, is going to be a local maximum, and that's because we went up and down. Then we go down and up, so that's going to be a local minimum. A local minimum is occurring when we plug in 2 into the original function. So plug 2 in here, we get 8 instead. 2 here, we get minus 24 and plus 2. So 8 plus 2 is 10. Take away 24, we get negative 14. All right. All right, that's the first part. Now we're going to do the same thing for the second derivative. So I'm going to take my second derivative and set it equal to 0. Second derivative here is 6x equals 0. There's only one answer to that, 0. The second derivative doesn't exist. Well, that's not going to happen. It's a nice polynomial, so I only have one critical number. So that critical number, I'm going to leave this up here for now. And my one critical number is 0, so that splits my number line into two pieces. Pick 2 test points, one over here like negative 1, and one over there like 1. And I plug those into the second derivative. So what's f double prime of negative 1? What's f double prime of 1? So if I plug negative 1 into the second derivative, I get negative 6. That's a negative number. If I plug in positive 1 in here, I get a positive 6. That's a positive number. And since the second derivative is negative over here, that means the original function is concave down. And since I get a positive here, that means the original function is concave up. All right, so I can add to this information here, and I'll just add it right here, that my original function is concave up on the interval from 0 to the right, so from 0 to infinity. And my original function is concave down, those are arrows, from negative infinity to 0, so to the left of 0. I have an inflection point because this 0 is actually in the domain of the original function, so I actually have a point on the graph. I change from concave down to concave up here, that's an inflection point. So I'll put IP for inflection point. My inflection point is when I plug in 0 for x, and then I can come up here and figure out what the y coordinate is on the original function by plugging 0 in here and here. I just get 2. All right, now, this is everything that we have already done, okay? So there's nothing new here, but now I want to sketch this graph. So the way that I show students to sketch this is kind of a 2-step process. We're going to make a table first. So the table I make is going to start with the number line, like this. Well, you know what, let me lower this down just a little bit. Okay. Start with the number line. And on this number line, I'm going to put my critical numbers, both from the first and second derivatives. So on the first derivative, I had 2 critical numbers, 2 and negative 2. So here's 2. Here's negative 2. And then I also have the critical number from the second derivative of 0. So I'm going to put those here. And then from this from here, I'm just going to draw, I'm going to make a table. So draw up, straight up from there. And I'm going to put in here enough room for 3 rows. Okay, so 1, 2, 3. This first row is going to be representing my first derivative. The second row is the second derivative. And the third row is the original function. So let's look at what's happening to the first derivative on this row. So to the left of negative 2, my original function is going up. All right? And then between negative 2 and positive 2, that's from here to here, it's going down. So in this little box and this box, it's going down. And then from 2 to the right, it's going up. All right? And then to fill in the second row, I'm going to do the concavity. So to the left of 0, it's concave down. So if I'm to the left of 0, it's going to be looking like a frown. So down here, And then to the right of 0, it's going to look like up, like a smile. Then I'm going to look up to figure out what these boxes are. And to do that, I look at these two pieces. So what is the only way you can go up on a frown? So you have two choices. You can have this side of the frown, or you can have this side of the frown. Well, it's obvious that if I'm on the left side of the frown, I'm going up, right? I'm going up as I'm frowning. If I were to be on the right side, I'd be going down, and I don't want that. I want to be going up. So it's these two pieces of information together tells me my original function over here has to look like the left side of a frown. And then here I have to go down the frown, which means I'm going to be on the right side, so it's going to have to look like this. And then here I've got to go down the smile. So on the smile I could be on the left side, or I could be on the right side. Obviously if I'm on the right side, I'm going up. I don't want that. I want to go down, so I'm going to be on this side. You can see I'm going down. So it's going to be the left side, and then left side of the smile, and then on this one I need to go up the smile, so that's going to be the right side. It's going to look like that. Okay, now once I've got that information on this table, what I'm going to do next is right below this, I'm going to draw my graph. So here's 0. I'm going to draw my number line again. Here's 0. Here's 2. Here's -2. And of course, I could draw my y-axis in here if I wanted. All right, so now I'm going to see if I can figure out the value of my function at these points. So let's plug -2, 0, and 2 into the original function. Well, it just so happens that we've already done that, okay? We've already figured it out. So like at -2, I had a local max of 18. At 2, I'm a local min of -14. And then at 0, I'm at 2. So let me do it this way. I'm going to count by, let's say, 5s. 5, 10, 15, 20, and then -5, -10, -15, and I don't need the -20 on there. So at -2, I'm at 18, which is about right here. There's a point on my graph. At 0, I'm at 2. At 2, I'm at -14, right? Yeah, like that. All right, now I don't have a ruler in here, so I'll make one. Okay, here's my ruler. So look at -2 here and go up to this chart. At -2, what you have to look like is this right here. This is what we need to look like. And it's going to connect to that point. So from here, it's going to go like this. Okay? And then between -2 and 0, it's going to have to look like this. So I'm going to go from here, shape the graph like this, and then connect to this point. Like that. Okay? And then between 0 and 2, I've got to look like this, and I've got to connect this point to this point. So I've got to look like the left side of the smile. And then when I go from 2 on, I've got to look like this. So the right side of the smile, and it goes up like that. So that's our general picture. In this section, we're not going to get into any more detail than that. In the next section, we're going to actually go and find, like, okay, look, obviously this is going to cross the x-axis somewhere. We're going to find the x-intercept. Here it's going to cross, find the x-intercept. We might have a function that has horizontal asymptotes. So there will be more involved in the next section. This section, we just want to figure out a way of turning this information into a picture, which is what I've done here. Local max, local min, inflection point. All right, pretty good. Let's take a look at number 27. Also, let me do something real quick. go. Number 27. Our function is 2 plus 2x squared minus x to the fourth. I think I'm going to time myself on this one. Okay, let's see how long this takes. All right, I'm going to need the first derivative. The first derivative of this function is just 4x minus 4x cubed. The second derivative of this function is 4 minus 12x. I'm going to first find the critical numbers by setting the first derivative equal to 0. That's setting 4x minus 4x cubed equal to 0. I notice I have a GCF. I can pull out a 4x, be left with 1 minus x squared equals 0. I recognize 1 minus x squared is a difference of squares. It's 1 plus x times 1 minus x. And I'm going to get three solutions: 0, -1, and 1. So x is 0, -1, and 1. All these points here live in the domain of this function because that's a polynomial, so these are all going to be nice points on my graph. The derivative doesn't exist. That doesn't happen because it's a polynomial. And now what I'll do is I will plot these. I'm going to go a little smaller here. Here's 0, here's -1, here's 1. This breaks up my number line into 4 regions. I pick a test point over here like -2, test point in here like -0.5, test point in here like +0.5, and test point here 2. All of these points get plugged into the derivative. So I need f prime of -2, f prime of -1/2, f prime of 1/2, and f prime of 2. All right, so let's see what happens here. If I plug -2 into the first derivative, that means I have to plug it in here. Now I could actually plug -2 in here, right, and get an answer. But sometimes it's a little easier to do it this way. So watch, I'm going to move this down. F double prime of x is 4 minus 12x squared. Okay, so what I was saying is if you rewrite this in its factored form, like that, it's much easier to see if we're going to get a positive or a negative number out. So take -2 and plug it in here. 4 times -2, that would be a negative number. Negative. And then plug -2 in right here. 1 take away 2, that's a negative number. And then 1 take away -2, be careful with that because we're putting a -2 in here. So 1 minus -2 is the same as 1 plus 2. 1 plus 2 is 3, that's a positive number. So you're multiplying negative times negative times positive. Negative times negative is positive. So positive times positive, this is going to be a positive number. That means that over here my original function is going up. Now you'll see the power of that in the next one, -1/2. 4 times -1/2 is a negative number because a positive times negative is negative. And then if I plug in -1/2 here, 1 take away 1/2, that's still a positive number. And then I have finally 1 take away -1/2 is the same as 1 plus 1/2, that's a positive number. And see, I'm not having to actually figure out the values. I'm just figuring out if it's positive or negative. This is going to be negative because these two together are negative. So that's a negative times a positive, that's still negative. That means my original function is going down here. And now let's plug in 1/2. If I plug in 1/2, 4 times 1/2, that's a positive number. 1 plus 1/2, that is going to be a positive number. And then 1 take away 1/2, that's another positive number. So it's switched again. F goes up there. And then finally, if I plug in 2, let's see, 2 here we get positive. 2 here we get positive. And then 1 take away 2, we get negative. So we get a negative number here, and that means my original function is going down. We have that f is increasing, and -1 was a critical, 0 and 1. So it's to the left of -1, so negative infinity to -1, unioned. It's also increasing from 0 to 1. All right, it's decreasing from 1 to 0. I'm sorry, -1 to 0. And then it's also decreasing from 1 on forever. We have a local max, let's see, wherever it goes up and then down. So up and down, and it also goes up and down here. So we have a local max at -1 and a local max at 1, but we need to figure out what the value of the function is there. So let's plug -1 into the function. -1 squared is 1, and then -1 to the 4th is 1. So we're going to have 2 plus 2, that's 4, take away 1, that's 3. And we get the exact same answer if we plug 1 in there. We get 3. And then we have a local minimum. Let's see, where it goes down and then up. So when we plug in 0, and if you plug 0 in here, you just get 2. All right. So far, so good. Now we're going to do the same thing we just did, but we're going to do it on the second derivative. So the second derivative equals 0 is 4 minus 12x squared equals 0. I can just divide everything by 4. 1 minus 3x squared equals 0. And then I can move things around. 1 equals 3x squared. 1/3 equals x squared, and then take the root. Plus or minus root 1/3 equals x. So I have 2 critical numbers here. I can put those on a number line. It's negative root 1/3 and positive root 1/3. These are critical numbers. So I need test points. So I could pick a test point like -1. I could pick 0 because between a negative and a positive, there's always 0. And then over here, 1. And if you didn't know what to pick, you could put this in your calculator, get it as a decimal, so you'd be sure that you're picking a number to the left of it. Same thing with over here. So I take these numbers, -1 and 0 and 1, and I plug these into the second derivative. Now it's a little easier to plug into the second derivative, so I'm not going to need to do anything. Just let's plug -1 in here. It squares, becomes 1. So 4 minus 12, that's negative. So I get a negative number here, which means my original function is concave down here. If I plug in 0, I get a positive number. So that means my original function is concave up. And if I plug in 1 again, I get negative. So my original function is concave down. I have that my function is concave up just between this and this. So between negative root 1/3 and positive root 1/3, my function is concave down to the left of negative root 1/3 and to the right of root 1/3. So negative infinity to negative root 1/3 union root 1/3 infinity. Whoa, whoa, whoa. All right, inflection point. I have an inflection point anywhere I see a change in concavity. So I see an inflection point here and here because I go from down to up and concave down to concave up and then from concave up to concave down. So I have 2 inflection points. One of them is at negative root 1/3. The other one is at positive root 1/3. And then what I can do is I can just plug these into the original function. So that might be a little bit of work. What is f of negative root 1/3? Well, it's going to be 2 plus 2 times, now if I square this, the negative times negative is positive, the root times the root goes away, so I just get 1/3. And then I have minus, now I need to raise this to the 4th power. So squaring it, remember, squaring it gave us 1/3. If I now square that again, which would be the same as the 4th power, I would get 1/9. So we get 2 plus 2/3 minus 1/9. Get a common denominator between all of these. So 9 is a common denominator. I multiply top and bottom here by 9. 18 over 9 plus multiply top and bottom here by 6. 12 over 9. I'm sorry, no, that's not right. Top and bottom by 3. 6 over 9. And then minus 1 over 9. So 18 plus 6 is 24. Take away 1, we get 23/9. So 23/9 is what we get here. And notice also, if we were to plug in the positive root, the same thing would happen because we're squaring and raising to the 4th. So we get the same exact effect. And so these are our inflection points. All right, time to draw. And really to draw, I use this table right here, this right here, and I use this right here. So I can erase everything else. Yeah, I don't think I'll need anything else. I should be able to squeeze this thing right in here, and I don't even think I'm gonna need that. So I'm gonna start with the number line up here. I'm gonna put my critical numbers. So from the first derivative, I have -1, 0, and 1. So -1, 0, and 1. And just so we know, as a decimal, where's my, okay. Just so we know what this is, where these points live, if I take 1/3 and take the square root, this is going to be -0.57, so this is -0.577, and that one of course is positive 0.577. So that just gives me an idea where they are. And because of that, I think I'm going to spread this out just a little bit. So let's say that 1 is like -1 is like right here, and +1, let's say, is here. And that means that -√1/3 is there, and +√1/3 is about right there. And then I'm going to give myself enough room here to go vertically here from there, so I can create this table. And I'm going to need enough for 3 rows. My first derivative information goes here, my second derivative goes here, and then overall what my function looks like goes up there. All right, from this, to the left of -1, I'm going up. And then between -1 and 0, I'm going down. So down here and down here. So from -1 to 0, I'm going down. From 0 to 1, I'm going up. So from 0 to 1, I'm going up. And then once I get past 1, I'm going down. Now the concavity, to the left of -√1/3, I'm concave down. So to the left of this, I'm concave down, down, down. Between this and this, I'm concave up, up, up. And then to the right of √1/3, I'm concave down again, down, down. And now we put those two pieces of information together. The only way to go up a frown is to go up the left side. So I'm going to look like this. To go down a frown, I'm going to look like that, the right side. To go down the smile is the left side. To go up the smile is the right side. To go up the frown is the left side. And to go down the frown is the right side. So those are my pieces of my graph. That's what they'll look like. And now underneath this, I'm ready to graph. So here's my x-axis. My y-axis is at 0. I've got √1/3. I've got 1 out here. Got -√1/3 and -1 here. Now I actually do know what these are as points. I had already plugged those in. I believe. I'd plug those in. Yeah, at -1 I was at 3. At 1 I was at 3. At 0 I was at 2. And at the roots I was here. And 23 over 9 is about this right here is about 2.555 forever. All right, so that gives me some idea of what my y-axis needs to be. The biggest number I'm going to get is 3. So I'm going to put, like, let's say 1, 2, let's say 3, like that. So at -1, I'm up here at 3. At -√1/3, I'm at 2.5555, something like that, so I'm here. At 0, I'm at 2. At √1/3, I'm up here at 2.555 again. And then at 1, I'm up here at 3. That's it right there. I really don't like that, but let's just stick with it. If I had to redo this again, I would move this x-axis down because I don't have any points down here, so I'd move it down so that I would get a little more room to draw things, but this should work. So to the left of -1, I've got to look like that. So connect the dot here and then draw that like this, arrow. Now between here and here, I've got to look like this, and I've got to connect these 2 points. Like that, okay? And then between here and here, I've got to look like this and connect those 2 dots. So like that looks pretty good. Then from here to here, I've got to look like this and connect those 2 dots. So let me do it this way. Yeah, pretty good. Then from here to here, I've got to look like this and connect those 2 dots. That. And then from here on, I've got to look like this piece and continue. So there we go. So you can see here, I have 2 local maximums, I have 2 local minimums, and 1 local minimum, and I have 2 inflection points. That's where my frown becomes my smile, and here when my smile becomes my frown. Okay, 16 minutes, 17 minutes. All right, wow, okay, 29 looks pretty ugly. I didn't even bother to check if that was in the video. I hope you can pick up on this detail. I know I'm writing kind of small. Pretty much up to this point, our functions have been nice. Polynomials are always nice to do this method on. It's when they're not polynomials that you start running into some issues. All right, so 29, x plus 1 to the 5th. Minus 5x minus 2. All right. This is a polynomial function. If you were to expand that out, that times itself 5 times, that would be a big polynomial. So I know the domain of this is everything. All real numbers. So let me get my derivatives. My first derivative is going to be chain rule on this and then derivative of each of those separately. So chain rule on that is 5x plus 1 to the 4th times the derivative of what's inside, which is 1. Minus the derivative of 5x, which is just 5, and then derivative of -2, which is 0. So that's not so bad. And then the second derivative, again, chain rule on this, so the 4 pops out, you get 20, and then x plus 1 to the 3rd, and then the derivative of 5 is 0. So that's your second derivative. All right, I think we can handle this. Let's take the first derivative, figure out where it's 0. So I take 5x plus 1 to the 4th minus 5, set it equal to 0. If I were doing this, I'd move the 5 over first. If I were doing it, I am doing it. Okay, and then I divide by 5. And now I take the 4th root on both sides. 4th root here, 4th root here, but when we do 4th root, or whenever we do an even root, we have to do plus or minus. So the left side, that's just going to become x plus 1. but the right side becomes plus or minus, the fourth root of 1 is still 1, so we get plus or minus 1. And now I need to subtract 1 from both sides. So I have positive or negative 1, then subtract 1. So this gives us two answers. If I do positive 1, take away 1, I get 0. If I do negative 1, take away 1, I get negative 2. So I'm going to have two critical numbers here. They are happening at 0 and negative 2. And so now I need to pick some test points. Negative 3 is a good test point, negative 1 is a good test point, 1 is a good test point. I plug these into the first derivative. And let's do it. Negative 3 into this guy. I think I can do this pretty easily. Let's see. Negative 3 plus 1 is negative 2. To the fourth power is going to be a big positive number. Times 5 is a big positive number. Take away 5. This is going to be bigger than that, so we should get a positive there. So positive number here, that means original function is going up. Now negative 1. If I plug in negative 1, I get 0 here, and that all goes away, and we just get the negative there. It's negative 5, so negative. So my original function is going down. And then at 1, if we plug in 1, we get 2 in here again, 2 to the fourth power. That's a big number, so that's going to be positive. So we get f is going up. All right. That means my original function is going up on the intervals negative infinity to, I forgot to box these, negative infinity to negative 2, and then union 0 to infinity. My original function is going down between negative 2 and 0. I have a local max. Let's see, do I have a local max? Yes, I have a local max here at negative 2. And let's plug negative 2 into our function and see what we get. So if I plug negative 2 into the original function, negative 2 plus 1 is negative 1. Negative 1 to the fifth power is negative 1. So I have a negative 1 out front, and then I'm plugging in negative 2, right? I'm plugging in negative 2, oh, right here. Plugging in negative 2 here. So negative 5 times negative 2, that's plus 10, and then take away 2. So we should get 7. Okay, and then as far as the local minimum, that's happening here at 0. And 0 should be easier to plug in. Let's see, well, maybe not. 0 in here, well, that's not bad. 0 plus 1 is 1. 1 to the fifth power is 1, so we get 1. 0 in there kills that off. Minus 2 is still there, so we get negative 1. All right. All right. Now I'm going to do the same thing with the second derivative. So second derivative equals 0 means I need to set 20 times x plus 1 cubed equal to 0. All right, this isn't going to be bad. Divide both sides by 20. Goes away. Take the cube root of both sides. You do not need to do plus or minus, but it doesn't matter because the cube root of 0 is still 0, and you just get x is negative 1. Also notice on both of these, I didn't look at where it's undefined, where the derivatives were undefined, because this is polynomial, so I'm not even worried about it. All right, so we have one critical number, and it's going to be the number negative 1. So let me pick negative 2, and let me pick 0, and let me plug these into the second derivative. So f double prime of negative 2 and f double prime of 0. All right, negative 2 into this. Negative 2 plus 1 is negative 1. Negative 1 cubed is negative 1. Times 20 is negative 20. So I get a negative number here, which means I'm concave down. My original function is concave down. And then if I plug in 0, I get a positive number, so concave up. All right. That means I have an inflection point here too. So first, this is concave up. Original function is concave up on the interval, let's see, negative 1 to infinity. F is concave down on negative infinity to negative 1. I have an inflection point at the point -1, and what would happen if I plug -1 into the original function? -1 into the original function right here. So that's 0, gone. -1 right here, we have -5 times -1, that's 5. 5 take away 2 is 3, so we should get 3. And that's it. That's it. Picture time. I'll erase all this. Do it right here. I don't need any of that. Oh wait, I did need that. That was at -2.7 was my local max. Okay. All right, so start off, number line. My critical numbers are going to go in here. I have -2 and 0, and then over there I have -1. So I'm going to go -2 here, -1 and 0. Give myself enough room for 3 rows. This first row is my first derivative, second derivative, then the function. All right, so here to the left of -2 I'm going up. And then between -2 and 0, I'm going down. Between -2 all the way to 0, right? Going down. And then to the right of 0, I'm going up. And then concavity, I'm to the left of -1, I'm down. So here's -1, I'm down, down. And then to the right, I'm up, up. And now just put them together. Go up the frown, left side. Down the frown, right side. Down the smile, left side. Up the smile, right side. And then draw this graph. Here's the y-axis, 0, -1, -2. So at -2, I'm up at 7. At -1, or sorry, at 0, I'm at -1, and at -1, I'm up at 3. So you know what? On this one, I'm going to think about it a little more. I'm going to do it this way. Just going to move this axis down since most of my points are above the x-axis, or pretty close to it. I'm just going to move this down like that. So here's 0. Here's -1. Here's -2. So at -2, I'm up at 7. So let's say 1, 2, 3, 4, 5, 6, 7. There's 7. So at -2, I'm right there. At -1, I'm at 3. That was my inflection point. 1, 2, 3. There we go. And at 0, I'm at -1. So at 0, I'm at -1, which is about right here. And now put it all together. So this point right here to the left of it, I've got to look like that. So it's going to go concave down like this. Between here and here, I've got to look like that. So I'm going to connect these 2 dots with the right side of a frown. And then from here to this point, I've got to look like the left side of a smile. And then to the right of 0, I've got to be the right side of a smile. Local max, local min, inflection. All right. Maybe I have time for one more. Number 31. F of x equals, they use capital F, I'm just going to use little f, x root 6 minus x. Okay, I'll use capital F. Fine. All right, well, this is our first non-polynomial example from what I've been doing today, where I've been trying to graph these. And so I do need to pay a little attention to the domain of this. I have a square root, and that could cause a problem. So let's just remember that when you have the square root, everything inside here, the radicand is what we call it, that radicand cannot be negative. So 6 minus x must be greater than or equal to 0, which means that if you solve this linear inequality, just move the x over, that means x must be less than or equal to 6, which on a number line would look like this. Here's 6, right? Anything to the left of that is good. So the domain of f is everything in the interval negative infinity to 6, but including 6. We could actually plug 6 into this and get 0 into there. Square root of 0 is just 0. So my function, when I draw it, should only exist on that interval. There should be nothing to the right of 6. And I also have to keep that in mind when I get my critical numbers, that they need to live in that interval. All right, so let's take our derivatives. Our first derivative is going to be, how about we do some product rule? Okay, so there's your product. Derivative of the first one is 1 times root 6 minus x, plus the derivative of the root of something, this is a chain rule, is 1 over 2 times the root of that something, times the derivative of what's inside, which is negative 1, and then finish off the product rule by bringing your x in. And let me clean this up. This is root 6 minus x, and then I'm going to have a minus, and the x is on top, so x over 2 root 6 minus x. Now that's my first derivative, and I can work with that. But because I know I'm going to need to set this equal to 0, and I have a fraction in here, I'm going to try and put these together with a common denominator. So I'm going to put this over 1, and that means I have to multiply this first fraction on the top and bottom by this denominator. So by 2 root 6 minus x on the top, 2 root 6 minus x on the bottom. I'm multiplying this thing by that, root 6 minus x over 1. And then over here, I'm not doing anything. And what I get, this new top here, the root times the root, since those are the same roots, the roots are going to go away, and I'm just going to get the 2 sitting in front of 6 minus x, but that is in parentheses. And then I have minus this x, and then all over my common denominator, which was 2 root 6 minus x. I distribute through here, so I get 12. Take away 2x, take away another x is minus 3x. And then all of that over 2 root 6 minus x. So that's my first derivative right there. That's a pretty clean version of it. So let me replace it in here. This first derivative is 12 minus 3x over 2 root 6 minus x. All right, that was the first derivative. The second derivative is going to be even worse. So to do our second derivative, we're going to have to use quotient rule. And so it's derivative of the top, which is just negative 3, times the bottom, minus the derivative of the bottom. Okay, the 2 is going to come for the ride. And then what's the derivative of the root of 6 minus x? Well, we did that earlier. We know it's going to be a chain rule. So it's 1 over 2 root 6 minus x times the derivative of what was inside of this, which is negative 1. So again, derivative of the top times the bottom minus the 2 comes for the ride. Derivative of the bottom is right here. Now I still need times the top. So in parentheses, 12 minus 3x. That's all over the bottom squared. So I'm going to square these individually. Since there's multiplication, 2 squared is 4, and then when you square the root, it goes away, but it has to be in parentheses. So 4 times 6 minus x. That looks really bad. All right, this is, put this together, that's negative 6 root 6 minus x. I'm going to say over 1 because I'm going to get a common denominator on the top. These two cancel. Minus and minus become a plus, so that becomes a plus. So plus, what's still left? On the top, I have the 12 minus 3x, that's this, and that's just sitting on top of this root. Uh, 6 minus x, like that. And then all of that is over 4 times 6 minus x. All right, let's get a common denominator between these two. That means I'm going to introduce the root 6 minus x here and a root 6 minus x here. So I get, let's see, the negative 6 there. The root times the root goes away, but I have to put it in parentheses. And then plus this thing, plus 12 minus 3x, all over the common denominator, which is root 6 minus x, but then all of that over 4 times 6 minus x. I'm going to do one more thing. I'm going to make this over 1, and then I'm going to flip like this. And when I flip, the 4 and the 6 minus x will join down here. So it'll be 4. And I'll just put 6 minus x here, and then the 1 would be on top, so it wouldn't change anything. And that would be it right there. That is almost cleaned up. I got to clean it now. Let's see, negative 36 plus 6x plus 12 minus 3x over 4 root 6 minus x times 6 minus x. All right, ready to write my final second derivative down over here. Just combine like terms on the top there. 36 take away 12 is negative 36 add 12 is negative 24. And look, 6x minus 3x, that's 3x, so I'll put the 3x first. 3x and then minus 24 is on top over this thing, 4 and then root 6 minus x and then times 6 minus x. By the way, you could put these two together. This root in that is the same as 6 minus x to the half times 6 minus x, and they have the same base, different exponents. You add the exponents, a half plus 1 is 3 halves. So you could, if you want, rewrite that as this over 4 times 6 minus x to the 3 halves. But I'll just leave it as that for now. Oops. I just want to check something as I proceed here. 3x plus 12. 3x minus 24. Okay, we're good. All right. Now, I should have timed this one. All of that was just to get my first and second derivatives. And now what I need to do is figure out where the first derivative is 0. And remember, a fraction can only be 0. That's the whole reason I simplified it, because this is nice to set equal to 0. The only time a fraction can be 0 is if the top is 0. And if you move things around, you get x is 4. Now, is x equals 4 in this domain? Yes, so that is a critical number. Now, I need to figure out if this first derivative doesn't exist. Well, there are some problems, okay? First of all, we know that 6 minus x can't be negative, but we've already kind of thrown that out because the domain already says that this underneath here can't be negative. But because it's in the denominator, it's possible to turn it into 0. If I let x be 6, right, I'm going to get 0 here. I can take the square root of 0, but the problem is then I have division by 0. So x equals 6 is a critical number because it causes division by 0. And 6 is in this interval, so I need to include that as a critical number. So now when I go to do this, I put my two critical numbers down here, 4 and 6, and that splits my number line into two pieces. I pick a test point over here, like 0 is a good one. In here, a test point would be 5. And over here, I'm actually not going to plug in a test point. Why? Very good. That's right, because the domain of f does not include anything to the right of 6. So I can't look over there. all right? So that's it. I'm just going to plug in 0 and 5. So what is capital F prime at 0, and what is capital F prime at 5? So if I plug 0 into the first derivative, let's see what happens. Up top I get 12. On the bottom, root 6 is a positive number. Times 2 is still positive. So I have positive over positive. That's a positive number. So my original function, capital F, is going up. And then at 5, let's see what happens. 3 times 5 is 15. 12 minus 15, that's going to be negative. 5 here, 6 minus 5 is 1. That's going to be positive. So I've got a negative here. So my original function, capital F, is going down. Bam. Got it. Okay, so I think for this one, because you kind of got the idea, if I want to say, where's F going up, I better do it. Hold on. So here's my conclusion. F is going up to the left of 4. And left of 4, I can go as far as I want because the domain is all the way. So I go from negative infinity to 4. And that's it. That's where it's going up. Capital F is going down to the right of 4, but you can only go as far as 6, right? Because the domain. So I'm going to say from 4 to 6. And we always use open parentheses on intervals of increasing and decreasing, even though the function stops at 6. Just leave it as open, and that's correct. We have a local max. It's occurring at 4, and that's because I go from up to down. And so at 4, if we plug 4 in here, nice. 3 times 4 is 12. That's cool. 3 times 4 is 12. And that gives me 0, and everything else doesn't matter. It's not 0 on the bottom, so that's just 0. Very cool. Local minimum? None. I never go from down to up. So I don't have a local minimum. Now, second derivative equal to 0. All right, so we look at this and we say, the only problem I could have, the only way that can happen and be 0 is if the top is 0. And that's 3x is 24. And that's x is 6. And so this is a critical number so long as it's in the domain. Oh wait, no, hold on. 24 divided by 3 is not 6, it's 8. Okay, but 8 is not in our domain, right? 8's outside. So that means I don't have a critical number for the second derivative. But this thing is either concave up or concave down. It's one or the other. You can't really be neither one. I suppose you could be, your second derivative could always be 0, but in this case it's not. So what we need to do to figure out the concavity is this. Here's 6. We know we can't go past 6, right? Can't go this way. I'm just going to pick any point over here. Does not matter what it is. Plug it in and see what happens. So why don't we pick 0? That's a nice one. Let's plug in 0 and see what happens to the second derivative at 0. Whatever this is going to be what the function is on that entire domain. So if I take 0 and plug it in here, I get a negative number on top. 0 here, that gives me a positive number. 0 here gives me a positive number. So I have positive, 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 and on the top I get negative. So this is going to be negative, which means that my original function f is concave down to the left of 6 forever, okay? Because I had no other places, no other critical numbers. The only one that existed was over here at 8, and I throw that out, it's not in the domain. So I can say this, my original function is concave up, where? Never. So we put empty set. Where is it concave down? Well, on its entire domain, from negative infinity to 6. And again, you can use the parentheses there, and that's okay. All right. I think we're good. All right, I'm going to try and draw it.